Okay, so this may be a longer video. I'll try to go fast but not too fast. We're going to talk about all transformations. And so I didn't introduce this last time because I didn't want to overwhelm you with all the letters. But yesterday, or last video, we just talked about moving up, down, left, right. So our value of k is probably the easiest one. And so we see k represented here. So our value of k determines our vertical translation. So vertical occurs when it's on the outside of the function. So if k is positive, then we would go up that many units. So if it's plus 3, we would go up 3. If it's minus 2, we would go down 2. So if k is less than 0, if k is negative, then we would go down 0. If there is no number here, then it's 0. That means it doesn't go up or down. It just stays on the x-axis. Now, what about h? We talked about how that's the inside of the function. So here, now maybe you see why it's opposite of what you would think. It's because the formula says x minus h. So really, if I plug in h with a positive 4, I get x minus 4, and we think, oh, well, positive 4, wouldn't that go to the right 4? Well, yeah, you're kind of right. If I have h as a positive 4, when I plug in the formula, it looks like a negative 4 because it's x minus 4. And so that's why you have to kind of switch your brain around here. But anything on the inside of the function would be horizontal. So horizontal would occur when it's inside the function. So that's what we get here. So technically, if we have x minus 4, that 4 is positive because it's a greater than 0 kind of idea. And so it would go to the right 4 units. What happens here, though, when h is negative, when it's less than 0, it means it goes left. Why it does that is because if h is negative 3, then in my formula, I get x minus the negative 3, right? I would get x minus a negative 3. If I wrote it like that, you might be able to say, oh, hey, h is negative 3, therefore it's going to go left 3. I get it. But what happens when we have minus and negative together, it becomes a plus, right? So really, when h is negative 3, inside the absolute value, we would get x plus 3. So it looks like x plus 3. Sorry, these are absolute values. So that's why when h is a negative 3, it actually goes to the left. So when we see x plus 3, it actually goes to the left 3. So it's a little bit opposite of what you would typically think. So therefore, we're talking about horizontal and vertical. We did that already. Now, what happens with these other two letters? We have an A and a B. And so with A and B, it's really kind of carries some of the same thought process. Notice how A is outside of the function. When I say that, I mean outside of the absolute value bars. So because A is on the outside of the function, it's still vertical. So A is still vertical. Why? Because it's on the outside. So when the absolute value of A, meaning like if I had a negative 4, the absolute value of that would be a positive 4. So like if A is 4, that means we have a vertical stretch by a factor of 4. We're going to use BFO, so you don't have to write by a factor of every time. So by a factor of, or BFO-A. So if this is 4, if A is 4, we would have a vertical stretch by a factor of 4. What does this mean to stretch and shrink and all that? It'd be like if I had Play-Doh. If I brought a big tub of Play-Doh and I had a nice ball here, and I grab that Play-Doh and I vertically stretch, vertical is up and down, and I stretch that Play-Doh, it would get skinnier, right? No matter how wide it was, as I started to stretch it, it would get skinnier. And therefore, we have this vertical stretch. So my V shape, as I stretch it vertically, it's going to close. So the higher that number A is, then the more closed that V shape gets. In the same way, if I had this big tube of Play-Doh and I had a vertical shrink, meaning I'm pressing down vertically, there's nowhere for that Play-Doh to go other than out. Do you see? If I had Play-Doh, it would be coming out. So vertical shrink, pressing down from top and bottom, would make that Play-Doh come out. So in the same way, if I press down on this V, the only place it has to go is out. And so that is kind of where the idea of vertical stretch and shrink comes from. Think of like a big tub of Play-Doh, and as I stretch it vertically, what happens to the graph? As I push it down vertically, what happens to the graph? Now, what does this mean when the absolute value of A is between 0 and 1? I want to say just think of a fraction, but I want you to be careful because I know that the fractions we're going to be dealing with in here are going to be between 0 and 1. For example, like 1/2 or 4/5 or 2/3 or something like that, and that would be a vertical shrink. Where I want you to be careful is like, what if I gave you a fraction 5/4? Well, technically 5/4 is greater than 1. It's not in between 0 and 1. Now, I would never do that to try to trick you, so I would never give you a fraction that's greater than 1. I just don't want you to only think, oh, this is only fractions. But for our purposes, yes, when you see a fraction, you can assume it's going to be a vertical shrink by a factor of that. So for example, if a is 1/2, so if I had a fraction on here, 1/2, then this would be a vertical shrink by a factor of 1/2. All right, what about on the inside of the function? So horizontal means inside. So this is inside the absolute value bar, so that means we're going to have a horizontal shrink or stretch. So horizontal is on the inside, and we can use the word high to remember that. Now, if on the inside of the function we have a number that's greater than 1, it's flipped, it's backward of this. You would think, oh yeah, it was vertical stretch here, it must be horizontal stretch. No, it's opposite. The inside of absolute value functions has to be strings, doesn't it? So it would be a horizontal shrink by a factor of 1/b, or the reciprocal. For example, if b were the number 3, then this would be a horizontal shrink by a factor of 1/3, right? The reciprocal of 3, or any whole number, is 1/that. There was one more thing. I lost my train of thought. It'll come back. So horizontal shrink. What is different about horizontal shrink is exactly the same thing as a vertical stretch of what it does to the graph. So remember, vertical stretch, I take my Play-Doh and I stretch it. What happens to that V? It gets stretched, so it gets smaller. A horizontal shrink, then, is where I have this big lump of Play-Doh and I'm pushing in from the left and right. So I'm shrinking it from the left and right. Well, what's going to happen to that Play-Doh? It's going to go up and down. So for example, if I had a V-shaped graph and I push in from left and right, it's going to close and it's going to be getting skinnier, right? So actually a vertical stretch is the same as a horizontal shrink. Very interesting. Also, a vertical shrink is the same as a horizontal stretch in terms of what it does graphically to the function, in terms of what your eyes can see. Again, let's take a look at this, talking about a fraction again. If I have a fraction on the inside of the function where b is located, then I can assume it's going to be a horizontal stretch, but you want to just double check to make sure the fraction is something like 2/3 and not, something that's larger than 1, like 6/5. Okay, horizontal stretch. Now, in the same way with the Play-Doh example, a horizontal stretch, if I had this big lump of Play-Doh and I stretched it left and right, if I stretched it horizontally, what happened to that graph? So if I had this and I started pulling it left and right, it would open up. So do you see how a vertical shrink, which makes it open up wider, is the same as a horizontal stretch, which makes that open up wider? So they do the same thing, it's just their location may be different. You're going to want to write this down. If you're in my class, I will give these to you as notes or post it on the Google Classroom. If you want to pause the video so you can try to write these down, that might be a good idea. Okay, I skipped 2 things on purpose. Now, let's talk about what if they are negative, because right here I have absolute value, absolute value, absolute value, absolute value, meaning we're not really dealing with negatives. Now, what if it is negative? If it's a negative number on the outside, what's going to happen is it's going to flip the graph. So instead of a V-shaped graph pointing up, it's going to become a V-shaped graph that points down. In the same way, what's going to happen over here, if B is negative, this is kind of nice, it's convenient. If B is negative, it's going to reflect over the y-axis, where the first would open, instead of opening up, it reflects over the x-axis to open down. Here, it's going to reflect over the y-axis, but if I have a V-shaped graph and I flip it over the y-axis, it's still a V-shaped graph. So actually, for parabolas and absolute value functions, we don't really have to worry about that as much, but other functions like cubic, you would want to pay attention to that. So, good news is, out of everything in this list, it's a lot of letters, it's a lot of directions. The one that you don't have to worry about as much is going to be B right here. But, okay, let's go ahead and do some examples. Sometimes just getting some examples in is going to make it a lot easier. So I want you to remember two things. Vertical means we're going to be on the outside of the function, whether it's shifting up, down, or whether it's stretching up or down. Horizontal, whether you're shifting left or right, or whether you're stretching it or shrinking it, is going to be on the inside of the function. All right, I want to do 3 examples. So, number 1, we're going to use blue to represent number 1. F of x equals 2 times the absolute value of x minus 1 and then plus 3. So let's deal with the easiest one. We have an a, b is technically 1, so we don't have to worry about that. We do have an h, and we do have a k. All right, easiest one first, plus 3. I'm going to start here, I'm going to go up 3. So remember, my parent function is this origin. I'm going to go up 3. So from the origin, 1, 2, 3. Now, what about left and right? What is my left and right shift? And I'm just talking about the vertex right now. But x minus 1, okay, that's on the inside of the function. I'm using the word high, so inside, oh, that's horizontal. Okay, but this one's the weird one. This is where it's opposite of what you would think. So I see x minus 1 actually means I go to the right 1. Okay, so I'm going to go up 3 because it's outside of the function, so that's vertical, so it's up 3, and then right 1. So my new vertex is going to be right here. So starting from the origin always is where the parent function starts. We're going to go up 3 and then to the right 1. Now, what about a? So we took care of k. That's usually the easiest one. Took care of h. Now what about a? So a is 2. It's a positive 2. And this is on the outside of the function. So remember, vertical is outside. So outside of the function. So this is going to be a vertical stretch or shrink. We just have to figure out which one. If you refer back to your notes, when a is greater than 1, we have something larger than 1, this is going to be a vertical stretch by a factor of 2. So one thing that we could do is we could say, okay, this goes up 3, this goes to the right 1, and this 2 here, this is a vertical stretch, and we're going to say BFO by a factor of a, which a is 2. So this is a vertical stretch by a factor of 2. Now what does that mean graphically? I get up 3 and I get to the right 1, but how the heck do I draw that? Some teachers aren't going to like that I say this, but that's all right. We're going to typically look at this, for absolute value functions at least, as the slope. So think of this 2 as being a slope of 2. So from this point, if I have a slope of 2, I'm going to go up 2, right 1, up 2, right 1, up 2, right 1. Now, because it's absolute value, and we know that the general shape of absolute value is this V shape, that means if I go up 2, right 1, and it reflects over this point, this vertex here, then instead of up 2, right 1, to find the other side of the V shape, I can go up 2, left 1, up 2, left 1, up 2, left 1. And I still have that V-shaped graph. So notice, if this is our parent function here, and it would kind of look like this if I were to graph it. Notice how not only did it come off the board and it went up 3 to the right 1, but notice how it closed a little bit by this factor of 2. Okay, number 2. Let's take a look at that. Let's just keep graphing. I'll leave that parent function on there. Number 2. Again, the easiest in my opinion is looking at k. So on the outside of the function, what does that mean? Oh, that means that goes down 1. You're absolutely right. So I'm going to use purple for number 2. So this goes down 1. All right. Boom. So from there, down 1. Now, does it go left or right? Yes, because so this was down 1. Here, that is like saying x minus a negative 4, right? Which is why it turns to x plus 4. So remember, think opposite. If we see x plus 4, this actually means, hey, we're going to the left 4. So I'm going to go left 4. So down 1 and then left 4. 1, 2, 3, 4. So here is my new vertex. So it's like lifting this off. I'm going to go down 1, left 4. Boom. Now I have to figure out what the V looks like. This is on the outside. So this is our A on the outside. So that means we have a vertical stretch or shrink. It's a number in between 0 and 1. It's a 1/4, which is 0.25. So this is a vertical shrink. And we would say by a factor of A, which is 1/4. By a factor of 1/4. So what I can imagine, because it's a shrink vertically, if I press down on that Play-Doh, we should imagine that this V shape is getting wider. So if I have a V shape and I'm pressing down, it should get wider, theoretically. How does that look? How do we graph it? Well, think of that as slope for absolute value. So from 1/4, I'm going to go up 1, right 4. Boom. Up 1, right 4. Now, again, we know that this is just this part of that V. What about the left side of the V? So up 1, left 4. 1, 2, 3, 4. Up 1, left 4. 1, 2, 3, 4, somewhere around here. So here is the left side of that V. And it makes sense. If this is our parent function and we said a vertical shrink makes it wider, notice how this V shape is getting wider. And again, if you have a graphing calculator, use that. There's no shame in relying on that just to kind of double check yourself. The issue is on a test like ACT test or on a test in class, you may not have enough time to plug all of these in and then look at the table and graph it all. So being able to recognize this is going to make it a lot faster so you can make sure you get finished with the test. So you don't want to rely on the calculator, but you can use it as a tool, as a quick check if you're unsure, maybe on the ACT test or something like that. All right, number 3, going to do this in black. Now we have +5. Remember, it's on the outside, so it's vertical, so it means we're going to go up 5. So from this origin, I'm going to go up 5. So 1, 2, 3, 4, 5. Now, what about left and right? Here's the inside of the function. Notice how I don't have like a +4 on the inside or a -1. There's nothing there. That means I don't move horizontally at all. So it's like going up 5 and left and right 0. So I went up 5. Now, I don't have really anything on the outside. I have this negative. We're going to deal with that last. This negative on the outside, if you look at your notes, remember this means it reflects or flips. So reflects over the x-axis. So we're going to keep that in mind. Just take a mental note of that. On the inside, though, because it's on the inside, oh yeah, inside is high, so horizontal on the inside. But man, that horizontal was confusing because it's kind of backwards of vertical. I thought I got vertical, but horizontal. Okay, so this is going to be, let's see, a horizontal stretch. So if I look at my notes, it's 1/3. That's in between 0 and 1. Okay, so that's going to be a horizontal stretch. Oh, I'm sorry, that's vertical. Still used. It's going to be a horizontal stretch. So we're going to take that parent function, stretch it left and right. And so when I do that, it's going to become wider. So it's going to get wider. So this is a horizontal stretch. So this 1/3 means I'm going to have a horizontal stretch. Oh man, but by a factor of, gosh, it said 1/b. How the heck do I do 1/, a fraction? Remember, it's the reciprocal. So instead of, if my b is 1/3, the reciprocal of 1/3 is 3/1 or 3. So this would be a horizontal stretch, so horizontal stretch by a factor of 3. Okay, again, what does that look like? Well, that means, think of it as slope. So we have a slope of 1/3. So from here, I would go up 1, right 3, up 1, right 3. And then I would mirror that because we know it's symmetrical about the vertex. However, the issue is this negative out in front. What does that negative mean? Oh, it means we reflect over the x-axis. So this graph, instead of pointing up, it actually reflects. It's going to flip, so it's going to point down. So instead of going up 1, right 3, because it's being flipped over, we're going to go down 1, showing that reflection. Down 1, right 3. Down 1, right 3. Now, because our graph opens down, to mirror that, I would go down 1, left 3, down 1, left 3. And let's see if this even makes sense. That's a lot. Okay, I get the up 5. That's easy. Got that. This 1/3 thing. Okay, 1/3. We said it'd be a horizontal stretch, so it should get wider. Well, this does. That is wider than the parent function, even if it's harder to see. It's definitely wider. And then it reflects. It flips over the x-axis because of that negative. And did that happen? Yes, we're pointing down. So instead of the graph pointing up, this new graph is pointing down. That is a lot. It's going to take practice. You're not going to be able to get the hang of it just after 2 or 3 examples. So please try to find something. Khan Academy, do extra examples online or on your homework or worksheet or in ALEKS or whatever program you use. but this is going to take a lot of practice. And so after a while, you start to get used to it. I would suggest looking at your vertical up and down first, then looking at your horizontal, like left or right on the inside. Once you get those, that's your vertex, and then you're done. You're done with those two things. Then look for your A and B, and try to get used to remembering stretch, shrink, what does that mean, what's it going to do. For absolute value, at least, we can think of that as slope. And then pay attention, are these positive numbers on the outside, or are they negative numbers on the outside? Positive, my graph's going to open up. Negative, it's going to flip, and it's going to open down. I can't do that. Down. Go Tigers. Oh, you might be wondering, where's my girl? There she is. You're welcome.